All right, I'll start recording and then we'll jump into it. Looking at the schedule, it looks like we are to talk about section 8.4 today. But before we do that, are there any questions on anything we've covered in chapter 8 thus far? Okay. Well, in chapter 8.4, we're talking about polar coordinates and graphs. So I'd like to go over to Desmos and talk a little about graphing and polar coordinates versus our Cartesian coordinates. Everything we've done thus far has been in a Cartesian coordinate system with an x and y axis, much like you see on the screen here. And polar coordinates changes that up. I'm going to come up here to the wrench and change the graph settings. Notice that under the grid, we've got the option for a Cartesian coordinate system or a polar coordinate system. Clearly, things are circular here rather than squares, and I'm going to switch over to degrees since I'm a little more comfortable with that. So this is our polar coordinate system. And so it's a little bit different, but it fits a little better with the idea of the unit circle and looking at our triangles as portions of our unit circle. So now I'm going to switch over to Photoshop where I have a screenshot of Desmos, and I'm going to talk a little about what we've got here. Rather than calling this the origin, we're calling that the pole. And rather than call this the x-axis, we call this the polar axis. And it's really just the positive x-axis portion. And so when we graph points in a polar coordinate system, what we're graphing is r and theta, where r is the distance from the pole and theta is the angle from the polar axis. We've measured theta regularly, starting at the positive x-axis and rotating counterclockwise for positive. And we'll do the same thing here. So if I were to graph the point for 30, I would first start here at the polar axis and rotate through 30 degrees, and then move a distance from the pole of 4, and I would get that point right there. That is the point for 30 degrees. Say I've got a point over here. Let's go right there. That is a distance of 5 units. And the angle is halfway between 120 and 150, which would be 145. No, 135, I'm sorry. So that's 135 degrees. So that's how we measure and graph these polar coordinates. Now, I'm going to throw a little wrench in the works here. I'm going to come over to that point right there. That very clearly looks like it's 4 units away from the pole, and it's at an angle of 210 degrees. And the wrench I'm throwing in is that this is also -4 at 30 degrees. So thinking about this -4 at 30, we rotated through 30 degrees and we moved a distance of -4 from the pole. So rather than moving along the 30-degree angle a distance of 4, we move along that same angle but a negative distance. So there are multiple ways to denote these points. Either a positive distance, which means you're moving actually along the angle that's written, or a negative distance, which means you move the other direction from the pole that same distance. So a
So
couple,
I got a question real quick.
yeah,
Does that apply with that 135 degree? Would that be considered a -5 and then whatever the degree would be?
it is. Yeah.
Okay.
So it would be -5, and it looks like 315. So all of these points could be the same thing. This 4 at 30 could be -4 at 210. All of these points have multiple ways we could write those.
Can
Which is
you,
both good and bad.
sorry, could you explain how you get the -5, the number 315 degrees?
Yes. Let me come back in here. Let me change color so I'm not confusing things too much. So this angle right here, which would extend out there, it's halfway between the 120 and the 150, which is a difference of 30. And so I just added 15 to the 120 to get the 135. But if I extend that further down through the other side of the circle, I see that it's between the 300 and 330, a difference of 30. And so I just added 15 to the 300 to get the 315. So it's as if, let's see if I can change color again, as if we rotated through the angle of 315 degrees, and then rather than move +5, we moved -5 to put the point. So that's how I got the 315, was I just extended that blue line out to the other side of the pole and saw that that was at that angle of 315.
So every angle that we do is going to have a positive and a negative, essentially.
It could. Now, normally we're not going to look at both of those, but conceivably every point has at least two different ways to write it. Kind of like coterminal angles, we had lots of different angles that ended at the same spot. This is similar to that in that we have multiple ways to say the same point. We did the same thing with bearing, where we said, say, north 15 degrees east is the same as a bearing of just 15 degrees. Or if we were measuring from the positive x-axis, it would have been, what is that, 75 degrees. Three different ways to denote the same angle. So we're doing something similar here. So that's for plotting points. And Desmos does not allow plotting of points in the polar coordinate system right now. They're working on adding that, but they don't have that. And because of that, I went ahead and brought it into Photoshop so that we could plot those points in here and see what we were doing with that. But now let us go ahead and talk a little bit about converting from rectangular to polar coordinates. So just like some of the other work we've done, built off of this triangle idea in the first quadrant. We had some distance r out to the point, and that point had a given x and a given y. We had some angle in here. So cosine of theta is adjacent over hypotenuse, which is x over r. So if I were to solve for x, I could say that x equals r cosine theta, just multiplying both sides by r. Sine of theta would be opposite over hypotenuse, which is y over r. Multiplying both sides by r, we see that y equals r sine theta. And we also looked at tangent is y over x. And so we've got those relationships in place, and those will help us. We also know that Pythagorean theorem would suggest that r equals the square root of x squared plus y squared. We could also say that r squared equals x squared plus y squared. Again, Pythagorean theorem. We've used all of these before. Now we're going to use those when converting from rectangular to polar coordinates. So let's see what I'm talking about when I say that. So if I've got the point 3, 3, and I'm asked to convert that to rectangular coordinates, or to polar, so I need to take that to polar. Well, I've got an x and I've got a y. And so what I need to do is use these relationships that I've got over here, and I can find r. That would be the square root of the sum of the squares. So this would be the square root of 9 plus 9, which is the square root of 18. Well, that's like 3 root 2. So I know what r is. I need to figure out theta. As it turns out, if I were to plot this point 3, 3, sometimes that's the easiest way to do it. That point is right there, and the angle that's created, I've got 3 here and 3 there. We can clearly see that this angle would be 45 degrees because I'm up in the first quadrant at the point 3, 3. So theta equals 45 degrees. Well, now that I know r and I know theta, then converting 3, 3 to polar coordinates, that would just be r theta. So 3 root 2, 45 degrees. That would be the exact same thing as the point 3, 3. It would be at the exact same spot, just written in a different coordinate system.
Seems like a lot of work to get a simple answer.
It does. It does seem like a lot of work, but there are some things that are actually much simpler in polar coordinates than in rectangular. Let's take from polar to rectangular, just kind of to expand this one idea, and then we'll get over to some of those that are easier in polar coordinates. Let's now take a polar coordinate point, say 10 and pi thirds, and I need to convert that to rectangular. So I've got r, I've got theta. We know that x equals r cosine theta. So that would be 10 times the cosine of pi thirds. Cosine of pi thirds from our unit circle, you probably already have that memorized, is 1/2. And 10 times 1/2 is 5. So that's our x-coordinate. Y equals r sine theta. So that would be 10 times the sine of pi thirds. The sine of pi thirds is √3/2. And 10 times √3/2 is 5√3. So that would be our y. So now I know that the rectangular coordinates for the exact same point, 10 pi thirds, is 5 and 5√3. So if I were in Cartesian coordinates to go to the point 5√3, I would be at the exact same spot that I was when in polar coordinates I went to the point 10 pi thirds. So now we've converted from rectangular to polar and from polar to rectangular. But we really see the beauty of this when we go to equations. And so I want to go ahead and go to that now. Let me see if I can do this without I want to keep those equations around that I had before. I should have just gone to another layer. But we've got those equations. So let's keep those around for a minute. So now let's convert x squared plus y squared equals 25. If I were to graph that, we recognize that that's a circle with a radius of 5. Just from our familiarity with the equation of a circle. I can go ahead and replace x with r cosine theta. And replace y with r sine theta. I can go ahead and square these. So I've got r squared cosine squared theta plus r squared sine squared theta equals 25. I could factor r squared out. This is an identity that we're familiar with. Cosine squared plus sine squared is 1. So I end up with r squared equals 25, which means that r equals 5. That is a much quicker, easier way to write the equation of a circle than this one we had up here. I mean, only had to write 3 characters instead of 6. Half the writing. But now that one's much simpler. Anything that's kind of circular like that is going to look a lot nicer in polar coordinates. Things that are more linear will look better in Cartesian coordinates, as you might imagine. We can do one of those since we're here. 2x minus y equals 5. We know this is a line. It's got a slope of 2, a y-intercept of 5, and so on. But we could convert this over to polar coordinates by replacing x with r cosine theta and replacing y with r sine theta. We could, if we wanted to, factor r out. We would have 2 cosine theta minus sine theta equals 5. And that would be the equation of the line, 2x minus y equals 5. Clearly not as compact and simple as we had in our Cartesian or our rectangular notation, but it does give us the exact same line when we graph it. Do you have any questions on any of that? All right, well, there we converted 2 equations from rectangular to polar. As you might imagine, we'll need to convert some polar equations over to rectangular equations. So let's do that now. Layer in here. What I need to do. All right. Wasn't thinking ahead, or I would have had just those equations on their own layer. All right. So let's take a polar equation. Say r equals 4. That is clearly a circle of radius 4 in polar coordinates, and I need to convert that to rectangular. That's hopefully an arrow. Okay, so r equals 4, but we know that r equals the square of x squared plus y squared. So I would go ahead and square both sides to get rid of the square root. And when I do that, I get x squared plus y squared equals 16. And that would be the equation of a circle with radius 4. Simply plugging in where appropriate to get x and y, because our rectangular equations have x and y in them. Our polar equations have r and theta in them. That's the big difference. I should write that down. Polar have r and theta. Rectangular have x and y. So if I ask you to give me an equation in polar coordinates and you leave x or y in there, you haven't converted it completely. If I ask you for rectangular and you leave an r or a theta, it is not completely converted. You need to make sure that polar coordinates only have r and theta, and that rectangular only have x and y. But once you get that in, get those conversions done and simplify it as much as you can, then you're doing fine. So let's look at another one. Maybe one that's a little tougher, perhaps. R equals 2 cosine theta plus 3 sine theta. And we need to take that over to rectangular coordinates. So it'd be, in order to get x or y, I need r cosine theta. To get x, I need r sine theta to get y. And I don't have the r with either of those. So what I'm going to do is I'm going to multiply everything by r. And when I do that, I will have r squared on the left. I'll have 2r cosine theta. Whoa, that was weird. Okay, 2r cosine theta. What did I lose? I said it. I tried to write it, and it's not letting me write. Let's see if I'm on the wrong layer or something. I'm writing in white.
I would say you're writing in white.
Yep. Okay. So r cosine theta plus 3 r sine theta reminds me of a joke. Somebody said their yellow ink wasn't working in their printer, and IT tried to work it out on the phone, and finally IT said, well, I'm on my way, and they went up there and saw that they were printing on yellow paper. All right, so r cosine theta is x, r sine theta is y, and r squared is x squared plus y squared. And so substituting all of those in, x squared plus y squared equals 2x plus 3y. And there's really not much we can do to simplify that. So that would be the rectangular coordinates, or rectangular version of the formula that was r equals 2 cosine theta plus 3 sine theta. And so we've converted that over. Multiplying by r gave us that option because then we had r cosine and r sine, which we could replace with x and y respectively. And we had r squared that we could replace with x squared plus y squared. So looks weird. And just keep in mind that we want to keep coming back to these initial formulas wherever possible. We want the r cosine theta and r sine theta so that we can replace those with x and y. We want r squared to be x squared plus y squared and so on. And that allows us to replace those and get them in either rectangular or polar coordinates. You know what, I should probably zoom out so we can see more of that at once. Do you have any questions on those?
So is this all the chapter consists of, is converting between polar and rectangular?
There is just a little bit more, and I'm going to jump over to Desmos to show that, and that's the graphing of these. But that really is the only bits in the section. It's a pretty quick section. So I was silly to put it on 2 days in the schedule. In the future, I can definitely shorten that. But that'll give us a little bit more time to practice this before our next test. All right. So let me jump over to Desmos and we'll talk about the graphing of these. All right. Let's see. So we've seen that R equals 4 would be a circle of radius 4. We looked at that mathematically, and now we can see it graphically there on the screen. I talked about how kind of curved functions would look better in a polar system. Let's take a look at, say, R equals sine theta. And you can see that that would essentially be our unit circle, but just looking at sine. So the sine of 0 degrees was 0. And you can see that here on our graph, 0 degrees would be 0. And it works its way up to the sine of 90 being 1. And then back to 0. Now, what is the sine of 270? That's -1, right? And so if we rotate around to 270 and then move a distance of -1, we move the other direction and it's back up here at what looks like a +1. And that's why the graph is all above this y-axis, or what we would call the x-axis in our Cartesian notation. So let's look at r equals 3 sine theta. What do you expect to happen? It just lengthens it, moves it further away. So the sine of theta, when it's 0, 0 times 3 is 0. When the sine of theta is 1, up there at 90 degrees, we take that sine of 90 degrees, that's 1 times 3, now we move it up to 3. Sine of 180 degrees is 0, that times 3 is 0. The sine of 270 is -1. -1 times 3 is -3, so if you rotate around to 270 and then move a distance of -3, you're actually moving up from the pole instead of down.
Out of curiosity, how do you write theta in Desmos?
I open the keyboard here, and then I click the ABC, and it gives me theta over here on the right-hand side of their keyboard.
Mm,
And then
Thank
I
you.
copied it to my clipboard so that I could just paste it. Okay, and we've got pi over here if we need that. All right, so now let's look at, say, a double angle. So r equals sine of 2 theta. Well, look what we get. I'm going to clear some of these. I'm going to zoom in a bit. So sine of 2 theta looks like that. Let's look at sine of 3 theta. We get the blue one. Look at 4 theta. We get the green one. Let me turn these others off. So what's going on here? 4 theta gives me 8 petals. 2 theta gives me 4 petals. 3 theta gave me 3 petals. Let's see what 5 theta does. 5 theta gives me 5 petals. So what pattern are we seeing? You start back there at 2 theta, 3 theta, 4 theta, 5 theta. What do you see happening?
The even numbers double.
Exactly. So if we've got an even number in front of theta, we're going to have twice that number of petals on these flowers. If it's odd, then we get exactly that number of petals. Let's come out here and put a coefficient. What if we had a 2 here? So the 2 in front just lengthens the petals. Oh, that one's kind of hard to see now. So the number of petals fits that pattern we were looking at. So now you can see, just if you saw an equation that had sine or cosine in there, you can see that any number out in front lengthens the petals so that they are as long as that number. And then the coefficient to theta tells me how many petals there are. Same sort of thing would happen with cosine, only it's rotated. Well, and that fits with what we expect because the cosine of 0 degrees is 1. The cosine of 90 is 0. But notice we're doubling theta, so double 0 is still 0. If you double 90, you've got 180. If you double 180, you get 360. If you double 270, what do you get? 540. And so that's why it's doubling the number of petals. It might be nicer to see the odd one. So there's sine. Let's see what happens when we go to cosine. And it essentially rotated it. What looks to be about 45 degrees. Let me... Oh, it looks like it's more like 30 degrees rotated. And it all comes down to sine and cosine of those angles around the unit circle. So we could visualize these before we plot them, but sometimes it's nice just to come in an app like Desmos to plot. On the homework, I believe what they do is give you options and say which of these graphs would be the graph of 2 sine 3 theta. And so you would pick the appropriate graph. Sometimes they're a little odd. Say we had r equals 1 minus sine theta. We call that a cardioid because it looks kind of like a heart. Again, we could pick angles and plug them in and see what we get. An angle of 0 degrees. The sine of 0 is 0. So we would have 1 minus 0. So at 0 degrees, we expect it to have a distance of 1 from the pole. Sine of 90 degrees is 1. So if we plug that in, we get 1 minus 1, which is 0, and that's why it came back here. Sine of 180 is 0 again, so it would have a distance of 1. Sine of 270 is negative 1. And 1 minus a negative 1 is 2. And that's why it's down here a distance of 2 at 270. So again, I'm just kind of picking angles and plugging in their values, and that's why it plots out this way. You can always do that. You can always pick angles and plug them in and see what you get. Let's see. We've already done circles. You have any questions on any of these things we've talked about? The book doesn't go into much more detail than that. See, I'm thinking it might be kind of fun to plot the line that we figured out before. R times 2 cosine theta minus sine theta equals 5. Let's see if it'll do that. And there's the line that we converted from rectangular to polar coordinates. That was 2x minus y equals 5. So that would be y equals 2x minus 5. So it would have a y-intercept of 5, a slope of 2. Though it looks like the line curves because of the because of the circle. If you tilt your head, though, so that it's at the angle of the line, you can see it straight. But it does look kind of funny because of the way it moves on the curves. But that's the line we calculated before, the 2x minus y equals 5. So it does fit with all the stuff we've been looking at thus far. Have you any questions? You're probably wondering what the homework is like. And so at this point, go ahead and take a look at the homework. Start working through the problems. You may find them to be easier than you fear. Go ahead and practice those conversions from polar to rectangular and vice versa, using those basic equations that we had. Let me go back and share that again so that we can see those equations again on the screen. Of course, I don't have that up right now, so remember what layer it was I had those on. There we go. So don't forget that x equals r cosine theta, y equals r sine theta. Tangent is y over x, and r is the square root of x squared plus y squared. Those are what we will use to convert back and forth. And so practice those a little bit. I think you'll find the homework a little easier than perhaps you fear. But if you have questions, send me emails. And I will be in my office hours. Let's see, today at 3, and then again tomorrow morning at 9, and about 11:15. So if you have questions, you can come in and ask those. But I'm more than willing to help out in email as well. So if there aren't any questions, we could go ahead and call it a day. Right. Looks like we're feeling pretty good. Give it a shot, and have a good day. Take care of yourselves. Try to find some way to enjoy this. I just found out they extended the stay-at-home order for the state through April. I think that's what he said, until May 1st. So, or did he say the end of May? He extended it anyway. So do your best to stay sane, and let me know if you have any problems. Have a good day.
Thank you.
Thank you.
Welcome.